we're going to talk about all the shapes, all the types of shapes that you can encounter in your Smithy specs that you may want to use in your Smithy specs, what they mean and when would you use some of them. We're not going to get into the very specific details of each of these shape types, because for that I encourage you to check out the documentation, but just so that you know what tools you can use, what shapes you can use in your specs. That's what we're gonna do, just kind of a general overview. We're gonna have three main groups of shapes, of types of shapes. We're gonna have simple shapes, aggregate shapes, and service shapes. So yeah, let's get to it. So first of all, I mentioned simple shapes. Simple shapes are essentially the simplest shapes that you can possibly imagine. These are going to be our friends string, Boolean, integer, all the other numeric types, as well as blobs, documents, enums, and int enums, and timestamps. So let's walk through each of these briefly, just to get a vibe of them. So strings, I think we're all very familiar with. This is just UTF-8 strings, or just a sequence of characters in some encoding. Usually you're gonna have UTF-8. In case I didn't say that before, or you missed it from the previous videos, or you just don't remember, when we define a string using the string keyword, we just define a new shape of the type string, and we give it a name. We can attach some traits to it, so attach some behavior, some constraints, or some metadata. And this is different from like a string. If you were to use uppercase string somewhere, uppercase string is a concrete shape. It's just something that's defined pretty much like this. The standard library actually has a shape called string. So that's the difference, and let's get that out of the way. Then we have booleans. This is just true and false. Numbers, that's just going to be just integers and floating point numbers. Usually you would serialize them as some kind of numeric representation. So instead of like a string -5, you would have just -5 in JSON, for example, right? That's what we would use them. And of course, each numeric type can carry a different range of numbers. For example, bytes are going to be smaller than integers because you can only have so many bytes. I think byte has 256 values, so that's far less than the maximum integers that you can have. After numbers, we have blobs. So a blob is a byte array. It doesn't have to be like a string. It's just an array of bytes. So usually some kind of file could be a blob, or maybe some, you got some data, you don't even know what it is, you just know that there's a byte array of data, and you're just trying to like pass it forward to someone else, or you're trying to compress it with gzip or something like that. That's when you would use a blob. And in formats like JSON, this could be serialized as, for example, a base64 encoded array of bytes. So we're just gonna have a string. Then we have document. Document is a JSON-like AST. So it's either an object or an array of other documents. And documents can also have numbers, strings, booleans, nulls. So very much like JSON. This is basically isomorphic or equivalent to JSON, but again, it can be serialized in any way, not necessarily just JSON. But when your protocol is JSON, then that's what you're gonna get. Then we have enums. Enums are enumerations. So the typical default enum is a string enum. So your values of this enum are gonna be serialized as strings most of the time. So in this case, we have hello, goodbye, and good afternoon. You can provide a custom value of an enum entry, but you don't have to. So by default, the value is the same as the key, and the keys are these values here. So goodbye would be, this is equivalent to that. The Smithy spec actually considers enums as open. So if you have a value that doesn't fit into any of these alternatives, your client should still be able to decode that and to deal with this fact. In Smithy4S, that is not the approach that was taken, so it's kind of out of spec in here, because enums are considered closed by default in Smithy4S at the time I'm making this video, which is when we have 0.18 of Smithy4S. However, that was the default, but you can still opt out of this default by using the open enum trait from Alloy. And when you do that, your enum, your generated code for that enum will contain like a catch-all unknown case, which will capture this value that you get if it doesn't fit into any of these, so that you can still do something about it, maybe forward it to someone or do like a best match of sorts. So there's plenty of ways you can use that. And finally we have int enums. So this is exactly like enums, except you need to provide a value for each of them, and it has to be a unique integer value. So in this case I cannot have 1 and 1, I can only have 1 and 2. And these values of course also have to be unique, so I cannot copy normal enums value and reuse it between two entries of the same enum. And last but not least, we have timestamps. These are just instants in time. So for my Java folks, this is equivalent to an instant. This doesn't carry a time zone, although there are a couple encodings of a timestamp in things like JSON or HTTP, where some consumers can be able to parse a time zone, but they will convert to a normalized form, which is UTC basically. So I encourage you to read about this. There are 3 standard formats that you can serialize timestamps with. The protocol can define the default timestamp format, but most of the time what Smithy actually wants you to use is a numeric encoding of seconds since epoch, which is, to be honest, not very precise and maybe not the best choice of a timestamp format. So most of the time what I would do is say timestamp format is datetime, which is this ISO 8601 encoding. So the instant that you know. So that's it for simple shapes. Again, we have strings, booleans, numbers. These are like the basic building blocks of basically every program out there. Then we have blobs, which are maybe not that common in APIs, I think. Documents are not that common either, but very useful nevertheless, because sometimes you just want to capture like any JSON and carry it forward. Enums and int enums, I think mostly enums, are also quite popular and good for modeling some data types precisely, but we will soon see something even better for many cases, which is unions. We'll get to that in a second. And finally, timestamps are also pretty common. I think they appear in like every real-world API. So yeah, these are the types you can encounter, and there are just the simple shapes. Here's the link to the spec. You'll find much more detail about all of these. But for now, let's just move on to aggregates. Now, in aggregate shapes, we're going to deal with shapes that kind of wrap around other shapes. So these are going to be collections, but also tuples and unions, or products and co-products. Let's get into it. First, we have structures. So a structure is kind of like a Java record or like a Scala case class, and they are basically tuples, named tuples of things. So let's look at this one in particular. We have my structure, which has 4 members. It has a greeting, an addressee, created at, and an identifier. Only one of them is required. This is the greeting. So you always must have a greeting. That's the meaning of the required trait. Although apparently this is still kind of up to interpretation of this trait, and some protocols may decide to do things differently. So we have required. That's the only trait in here that I see. This is just a normal string. So what I mentioned before, this is just a Smithy API string, which is defined as a string shape of the name string. So that's the only required one. Then we have addressee, which is another string. This is the one we defined previously, which also has a constraint, but that doesn't matter much. Then we have created at, which is a custom timestamp. And finally, we have identifier, which is a string, but it has a default value. There are some semantics of what a default value means, but most of the time, or like for most protocols, this means that if you don't send this value, this is what you're gonna receive. It might even be required, and some protocols and some implementations of these protocols will still use the default value in case you don't provide a member of that name. So if you send a JSON payload, it's missing the key identifier, then you're gonna get an empty string. I think you can use any other string, but there are some limitations on what the default values can be. So for example, if the type was a struct, you cannot have a default value. So if you are missing the required field, most protocols will just reject the request and consider it a bad request. You'll get some kind of error message, hopefully a useful one. For optional things, you don't have to send them, but if you do send them, the type has to match, of course. So if it expects a number and you send a string that does not contain a number, well, I would say most protocols should fail that. So yeah, structures are just like case classes, records. Now we have unions, which are, I think, far more interesting than structures. A union is just one of these things, and it should be exactly one of these things. So if you have a union of these three, an integer, string, boolean, and also the fourth, my structure, if you see more than one of these keys in this record that you get as an input, that's not valid. You should only see one of them. So a valid JSON payload, for example, for this case would be I42. So the default encoding in most protocols is going to be tagged unions. We have the tag and then the value of that union member. There are other encodings that you could use, for example, untagged or discriminated unions, and they are available in some protocols, for example in Alloy, but this is objectively the best, and I encourage you to just stick to the default. It's going to be far more compatible with the other Smithy tooling that you use. It's a more efficient encoding for the decoding side, and it's far more flexible because you can have, for example, two members of the same type, and now you can discriminate between them. If you were to use untagged unions, you wouldn't be able to tell because they're the same type. And if you had discriminated unions, you can only do that if you wrap things in a structure anyway, so I think this is best. Moving on, we have sequences. These are just going to be things like a JSON array, so lists. They're ordered, at least the default lists, and by default they're not nullable. There's a sparse trait, which is already supported by Smithy 4S as well, which you can put onto your list. And then nulls will be allowed in the generated code. This would be possibly wrapped in like an optional type for the members of the list. And yeah, by default, you cannot send nulls. And lists can carry pretty much everything, like a structure, a union, another list. You cannot use the same list directly, because that's just not possible to construct then, other than an empty list. And now this is where it gets interesting. There's a trait called unique items. It's one of the constrained traits on the Smithy website. According to the spec, shapes with this trait are supposed to contain only unique values. But for example, in Smithy 4S, the current implementation allows duplicates. It will just get rid of them and convert to a set in the generated code. There also used to be a set shape, but oh, that's interesting. Yeah, it used to be there in Smithy 1.0, but now it's removed from the IDL. You can't use it anymore. But on the Smithy model, the kind of programmatic API of Smithy, it still exists. But my formatter actually rewrites this to a list anyway. So yeah, you can use unique items if you want to have like set semantics, but at the moment in Smithy 4S, it's not actually gonna enforce uniqueness, it's just going to get rid of duplicates. So now what your code receives has unique values. There are also some limitations on what the members can be, and I think at the moment the requirement is that the members of your collection must not contain any floats, doubles, or documents. Everything else is fair game. Apparently that's just something that is possible to kind of do the distinct operation on, or like check for duplicates on. In addition, in Smithy 4S, we have two extra traits that we can use to specify what the generated type should be. There is vector and indexed seek, so that you get a vector or an index seek respectively. Now here's the interesting part about all the aggregate shapes. They can be recursive, and they can also be mutually recursive. There's just one catch. Smithy must be able to tell that the recursion has a boundary, like you are able to actually construct values of this type, and the recursion is not infinite. So for example, you cannot have self-recursive required fields in structures. Let me see if I have a case for that. I do. So here, if you put required, that doesn't work, and this is validated right here in the Smithy LSP, but also in every other Smithy tooling. And unions can also be recursive, but you need like a case that is not just the same thing. So if I had this, that doesn't work, just a self-reference and no other cases of the union. But if I have some other case, for example, with a unit, then it's okay. In this case, what we're doing right here, we just have a union that refers to itself and unit. If you think about the values that you can construct here, it can be something like rec, and. If you do something like this, then you basically have an integer, right? You don't have any other data here. You're just saying that there's an and 3 recs around it. So it's actually like a non-negative integer. So this union is not very useful, but you can imagine that it would hold something else like structure, like what I think we had before. Yeah, so we first have a structure. This refers to the union now, and also to the structure, but you can also have other data in here. And this is much more useful, I think. So yeah, that's it about aggregate shapes. I hope that was clear. So to sum up, structures are like case classes, or just classes with these members. Unions are like a sealed trait in Scala or a sealed interface in Java. Kind of like a richer enum, because it's just always one of these cases. And the right-hand side can be just anything in the world. So it's like an enum connected with some extra data on that enum, okay? And then we have lists, so just arrays, well, collections. And I also forgot to write it right here, but we have maps as well. So let me show you this. We have maps, let's say string to number, key, string, value, integer. This is what a map looks like. Keys can be just string-like things, so I think you can only have a string or a string enum. And before I forget, there's one more thing in aggregate shapes that's really important. It's member shapes. So we talked about all these, like a structure, a union, and their members, but members are actually also shapes. So when we reference something like my structure here, we are in namespace aggregate, so this would be I could say aggregates my structure, and then we can specify the exact member, for example, this addressee with the $sign. So that's how you reference a member. This is also useful in a bunch of cases, especially when you work with the Smithy model programmatically, when you make some extra tooling on top of Smithy. But I think it's still good to know because it's a way to uniquely identify a given shape in a workspace. You just say the namespace, the aggregate shape, and then the name of the member shape in the structure. Or it could be in a union, or I'm not sure if we can actually refer to the member of a list.
Yes, it's possible.
So let's get into service shapes, or service types actually. If you go back to aggregates, structures, unions, lists, these three things are shape types, but a concrete thing like my structure, that's a shape, okay? So we have three types in the kind of service types group. We have services, operations, and resources. Let's talk about operations first. An operation is basically an endpoint. It doesn't have to be an endpoint in like HTTP, but it can be just some action that takes some input and returns some output. Optionally, it can also have errors. It can fail with an error. I'm not talking about errors today. This is going to be a separate video. And also input and output are also optional. You can have an operation with none of that, and that's also absolutely fine, although it's kind of useless. So you would most likely have at least one of these. An operation is pretty much always connected to a service, and by itself an operation doesn't have much meaning, but when you connect it to a service and call it within the context of that service, it has more of that. It has an input and output. These are not members like we thought, like we said about members here. Addressee, greeting, all that, ISB, these are members. Here it's not, it's a property. So it's different, it's important because this doesn't have a representation as a member shape. It's not a shape at all, it's just something that connects an operation with its input. But the input, the target of the input property can be and has to be a shape. There is another limitation here. The input and output have to be structures. You cannot have, let's say, an integer, although in some protocols, you can kind of work around this. For example, if you want to have an HTTP service that takes a string body, you can do it with HTTP payload, the HTTP payload trait. I may have covered this in a previous video, but if you have this, and let's assume our operation was an HTTP one, this would be valid, although we'd have to use a method like post. Then we have service shapes, finally the real service shapes. And a service is kind of like a logical grouping of 0 to many operations. We can have 0 operations, we can have 1, 2, 15, any number you can imagine. And we also have a version, which is, I think, optional. That's another property. And we have resources. I'll be honest, I don't know that much about resources, as I said in these comments here, which you can check out later, but they're kind of like a construct that's even more high level than a service. It is basically like a CRUD-like resource, a grouping of CRUD-like operations with like read, update, delete, and so on. There's properties for all of that. You can also have other kinds of properties. These are apparently like members of the thing that you're operating on. And there are also identifiers that can tell you which entity of that resource you're talking about. So again, not something I'm very well versed in, so I'm not going to talk about this in excruciating detail today. And also, it's not a coincidence, but Smithy doesn't support them. Really, what it does, it will just take a service's operations. When generating code for operations, it will also take operations from the resource. So that's pretty much as far as that support goes. And this is pretty much it. This is all I wanted to talk about. Just to sum up the service types, we have operations, so basically a function from input to output with possibly some errors. Then we have services, which group a bunch of operations and also these resource things. A service can also have a version, which is not really specified, like what the format has to be. It's basically any format that you want. And it's also not used very often by tooling. So I'm not really sure if we need this to exist, but it exists. And in some organizations, you can see people using it, for example, to mark a service with a given version so that when you change it, you can mark certain breaking changes. You still need to build a bunch of tooling on top in order to actually benefit from such version information. So again, a service is just like a wrapping of operations and also a connection to some resources, and resources are this magical thing that describes CRUD-like operations. So these are the types of shapes that you can see in your Smithy specs. I hope this is useful and it gets you going if you want to play with all these shapes. I did not talk about what they are represented as in like specific protocols. I did not always say that. Because it really depends on what protocol you use. As I said in the first video, just the shapes in your model, in the Smithy model, describe kind of structurally what data you're going to have, but the particular encoding and transport information that you're going to use is all up to the protocol. So I encourage you to check out the documentation for the protocol you are going to use and see what it looks like when you encode all these things on the wire. And this is it. Thank you for watching, and I'll see you in the next video.